Welcome to Statistical Computing with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at part 2 of R programming, where we'll cover scoping, reshaping, and plotting. So here's the Stat Computing website. I'm scrolling down to Chapter 6 and Part 2. The link will appear here. Here are the slides, and I'm going to page on down to the beginning of this lecture. Part 2. So here are 3 powerful programming techniques in R. Scoping, and we're going to look at the functions with and within. I'll be honest, in my standard programming practice, I never use these functions, but there are times when it is pretty convenient to use them. The reshape package, which I use all the time for manipulating data frames, in particular from going from between wide and long formats for data, and plier, which I use all the time, and we'll have a separate lecture on this. The idea is to take a data set, subset that data set by a particular variable, that is, split it, and then for each subset apply a function, and then combine all of those results. And it's very powerful. So here are 3 packages that we'll need for this part of the lecture. These are all packages by Hadley Wickham, formerly of Rice University and currently working for Revolution R, the folks who design RStudio. So the Reshape 2 package, beware. There are 2 Reshape packages, both of which Hadley Wickham wrote, and they are incompatible with each other. There is a Reshape package, and there is Reshape 2. So there are certain packages, for example, Galley, which allows you to create scatterplot matrices in Gplot. That uses the package Reshape, or at least it has at one point. But for the most part, you're going to want to use the Reshape 2 package. Okay, enough about that. Plier. Plier is, so PLY is the last 2 letters of the word apply, so to apply a function, and this is for R. And it just has the word ply because there are other letters that come before ply to do different things. And then, of course, Gplot. So let's talk first about scoping. Where does the variable live that you created? So let's start off by initializing a variable. N equals 10,000, right? So this is 1 times 10 to the 4th power. So this is a 1 followed by 4 zeros, 10,000. So we're going to create a data frame, and we're going to, the purpose of this data frame is to have the quantiles for the normal distribution, Poisson distribution, and gamma distribution using the Q distribution functions for normal, Poisson, and gamma. So we'll give a list of probabilities, basically from 0 to 1. And then we'll just calculate the quantile functions for these 3 distributions, and that will be the columns of our quants. Except I run this, and it dies. And let's try to understand why. So first of all, in this data frame, I've got a comment here. Why do we use a comma instead of semicolons? So we've got these commas here. So data frame is a function, and it takes arguments. And right now we're using 4 arguments. Each argument is an assignment of a column. So there will be a column in this data frame called PR, and PR is going to equal this sequence of numbers. So we're going to go from 1 to n minus 1, and we're going to divide that by n. So that will give us a sequence of numbers. And then what we're hoping to do is use PR, that sequence, as an argument in these functions, P norm, P Poisson, and P gamma, to create these other 3 columns, norm, Poisson, and gamma. And those are the arguments of the data frame function. Now notice we're using the equal sign in here, and that is about scoping. So this equal sign means that currently we are in this DataFrame function, and when I make this assignment of this sequence to the variable PR, that is a local assignment, meaning that it only exists inside the DataFrame that we're creating. It doesn't exist outside the DataFrame. And that is why the following lines fail to work. So when we get down to QNorm of PR, this argument here, it says that PR is not found because PR only existed in this little column and wasn't available outside of this function, outside the DataFrame function, to be used in this QNorm function. Okay? So the equal sign does a local assignment inside the function where you're working. If instead we had used this symbol, the left assign symbol, okay, less than hyphen, that would have assigned PR globally, meaning it would have existed not in this DataFrame function, but it would exist outside the function and would be available to be used. Okay? So anyway, that is why PR is not found when trying to run this command here. Let's go to the next slide. So let's go ahead and create PR outside. So this is right at the command prompt. I use the equal sign here, and that's going to assign it to the global environment, just as it would have if I had used the less than hyphen, that left assign symbol. So now PR exists. Now when I create my data frame, PR, I just assign it to a column named PR, and all these quantile functions work out. I'm going to remove the PR variable that I originally created, and just so it's not hanging around causing trouble for us, because ultimately we want the PR column within the quants data frame. So what does quants look like? You should already be thinking like the computer and creating this data frame in your mind. So I'm going to go to the next page and confirm our suspicions. Here is the function head. Head gives the top 2 rows, because I specified 2, of the quants data frame. And it has 4 columns, PR, norm, plus, and gamma, and it has the first 2 quantile values of that distribution. If I look at the structure of quants using str, we have 99 observations with 4 variables. Why do we have 9999? Let me page up for a second. Notice PR was created by going from 1 to n minus 1. So we didn't have 10,000, but we had 9999. Okay. So we have PR, which is numeric. Here are the first few values, norm, poise, and gamma, which are all also numeric. All right. Let's just look at the head of the Poisson variable. Okay. Oh, error. Why did I get an error? I got an error because poise doesn't exist in the global environment. It is a column inside the quants data frame. So I need to first specify the quants data frame and then the object poise. Okay? So there are 2 ways of doing that. The way that I typically do it is here. I will specify the quants data frame, and then the $ separates a hierarchy of environments. So I have the quants environment or list, and under that I have an object called poise. And you can't see these 2 values down there, but they're down there at the very bottom. It says 0, 0. Okay. Another way is to use the function with. With allows you to step temporarily into the environment. So we're going to step into the quants environment, and inside the quants environment there is an object called poise. And if we look at the head of Poise, there it is. It's these two objects. So with allows you, for one command, to step into a particular environment and operate in there. There is also a function called within, which allows you to do a little bit more. So here is the function within, and we're going to temporarily step into the quants data frame, and then from this curly brace to this curly brace, we're going to do a series of operations. The first thing we're basically doing 3 Boolean operations, looking at which of these 3 functions, the norm, the Poisson, or the gamma, are the largest. Okay? So if the normal quantile is bigger than the Poisson, and the normal quantile is bigger than the gamma, then the normal quantile is the biggest. So that is when this will be true. Otherwise it's false. If Poisson is bigger than both normal and Poisson is bigger than gamma, then Poisson is the biggest. Otherwise, if either of these is true, exclamation point makes this false. Otherwise, if neither of these are true, then, if this is false or this is false, then this whole expression is false. Therefore, the negation of that is true. That means the gamma one is the largest. Okay. We've done all that within the quants data frame. When we hit the close parenthesis here, we effectively update, well, we don't actually update the quants, but we're going to rewrite that to quants within, and that quants within will have the original quants variables in addition to the 3 variables that we just added. So we were able to reference the objects norm, Poise, and gamma directly without using, I'll page up for a second, without using this $sign notation of specifying the quants data frame each time. We were inside the quants and we could specify them directly. Okay, so now if we look at the first 2 rows of quants within, we have the original columns as well as these 3 gamma big, Poisson big, and norm big, which are trues and falses depending on which variable is biggest in the quantile. Okay, and tail gives us the last 2 observations, and here the Poisson is the biggest. Subset is something I use all the time. So remember how we removed this PR variable? Just making sure I wanted to see which values of PR was less than 0.1. I got an error because it didn't exist. All right. But subset knows where to look. So the way subset works is you specify an object, typically a data frame. And in this data frame, we're going to specify certain conditions, and subset will return the subset of rows and columns in the data frame that satisfy those conditions. So for example, in quants, I'm going to ask for all the rows where PR is less than 0.005, or all the rows where PR is greater than 0.995, greater than that. Okay? And so that will be returned into quants tails, and these are just the extremes. Okay? So if we look at the dimension of this object, I have 98 rows and 4 columns. Recall, quants has 4 columns as the PR column, and then it has norm, Poise, and gamma. So those are the 4 columns. In the 98 rows, well, there are 49 rows that satisfy this condition and 49 rows that satisfy this condition. Furthermore, we can use select or drop to specify which columns we want. For example, we have quants, that's our original data frame, and we're going to select minus Poise. that's a way of excluding poise. Return that to quants.sub, and so that subset does not have the poise column, but it has the other three. Okay, subset is super handy. You can specify statements like this simultaneously. So which rows do you want, which columns do you want, and so on. Okay, reshaping. I use this all the time. This is so wonderful. Okay? In the Reshape 2 package, there are two primary functions. One is melt, and the other is cast. You can think of this as sort of like metal. Okay? So think about when you need wide data sets. So for example, when you're fitting a linear model, you need a wide data frame. Your data frame has a column for each variable in the data set, and each row indicates a separate observation. We need long data frames when we want to plot things. And so a long data set takes a wide melting takes a long data set and reshapes it. Sorry, takes a wide data set and reshapes it to a long data set. Okay, so melt goes from wide to long. So here is an example of that. Quants is our data frame with the 4 variables, 9999 rows. I'm going to specify an ID variable as PR, and I'm going to melt the data frame. So this ID variable shows up, okay, down here, and we end up with 2 new columns. We have a column called variable, which now has a label in it for each of the 3 other columns, norm, poise, and gamma. And we have the value that occurred when probability was 1e negative 0.4. Okay, it's a little hard to see this right here. We're just looking at the first 3 rows. Let me page down for a second. Here is a summary of quants. Okay, that's what the original wide data frame had. There were 4 columns, and here's the summary of each column. Here's a summary of the data set in the long format. Now we have the probabilities. That's the same, though I'll tell you that there are 3 times as many rows here. Look at the variable. This variable column had norm 9999 times and also poise and gamma. It basically took these 3 columns in the wide data frame and it stacked them on top of each other. First we had the 9999 norm column, and all the numbers in the norm column ended up in the value column with the label norm inside the variable column. Then the Poisson column was stacked in the value column. All those numbers were here with the label under the variable column, poise, and then the gamma went under that. So that's sort of how I think about it. When you melt, you take each column and you stack them on top of each other, but you need to add an additional column, variable, which gives the label of which column the data came from. The default, let me page up again, the default labels of variable and value are a nice placeholder, but you may want to rename them. And there are lots of ways to rename columns. There is a function called rename, in which you specify the data frame, so quants.melt, and then the column in quants.melt that is called value, we're going to reassign that the name of quantile. So now if we look at quants.melt, the value column says quantile now. Okay, and so here's the new structure, and we have the quantile label on that column. All right, let's do some plotting, and I'm going to start off by showing you what can go wrong, and then I'll show you how to fix it. So we're going to start off by using Gplot and writing a function. All right, a little bit more about functions. So here we're going to use a function, or rather we're going to define a function called plot.quant. And it takes an argument x, which is the data set here, okay, or the data frame. Then it will automatically from that data frame assign PR to the x variable, quantile to the y variable, and then I'm going to plot a line for that quantile function. And the dot 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 is a special set of characters for a function that means and everything else. Okay, so this can represent multiple arguments, or it can represent no arguments. And those arguments, the dot dot dot, will appear here. So that means I could have a number of arguments and they would all go inside the geom line argument list. And the question here, how does R know where to find PR and quantile? Well, that's in the data frame already, X, that we're going to put there. Okay. If you pass this function plot.quant a data frame that does not have columns PR or quantile, this will not work. Okay, this is a very special function. It only works for the data frame we just created. Page down. All right, so now we're going to use our function plot.quant. Here is our data frame. It's our quants.melt, the long format of the quants data frame. And that's going to go into an object plot1. And let's look at that. And here is our figure. It maybe is not what you were expecting. I was hoping for 3 curves that indicate the CDF, not quite the CDF, the inverse CDF, the quantile function of my 3 distributions, the normal distribution, the Poisson distribution, and the gamma. What is happening? Well, maybe we need to pass some additional values. If I page up 1 second, to geom line and try to fix this. So let's start off by passing green to it. What if I color this green? Oh, well, that didn't quite give me what I wanted. What I need to do, I'll page down and show you the answer, is specify that the color of the line depends on which variable I'm looking at. And so here are my 3 variables, the normal, Poisson, and gamma. And that is the argument, the aesthetic of color equals variable. If I page up now, that is being put through this triple dot into this geom line argument. Okay? So that is where that is being applied. Let me page back down. All right, so what was happening in the previous plots? Well, what was happening here? So let's look at the function again. I'll page up. Geom line, okay, there's no arguments. For each x equals PR, it's going to plot the value y equals quantile. But I've got 3 separate functions. I have the normal, I have the Poisson, and I have the gamma. Which means over here, I start at the probability of roughly 0, and I plot, what am I plotting? I'm plotting the geometric object of a line. So I'm basically connecting points. So over here, I start with the normal value, and then I plot from there at PR equals roughly 0. I plot the normal value, and then I plot the Poisson value, and then I plot the gamma value. And so I've drawn 2 vertical lines at the same probability, close to 0. Then I increment slightly to the right to the next PR, plot the normal, Poisson, and gamma, and then I increment to the next one. So all this black is a ton of vertical lines. That's why the edge here is vertical, and this right edge over here is vertical, because you've connected the dots between the normal distribution, Poisson, and gamma distributions. And it's black. Yeah, it's black because the default is black. I page down. Great, I've turned all the lines green, but they're still vertical. At last, if you apply the aesthetic so that you have a separate color for each variable, then it effectively starts at the normal and plots the entire normal, connecting the dots only between the normal. Then it does the Poisson, which is the green jagged line, the step function. So that's what we needed. So if you ever get garbage like this, and if I had PR that was, actually this is worth doing. Another way that this can look, let me go over to R. And scroll down to where we're working with these functions. So I'll get down to this plotting function. Okay, I'm melting the data frame. I'm plotting it. Okay, let's go there, and we should end up with a plot here that looks like the one. Okay. All right, so the one thing I wanted to do is I wanted to change PR, or rather I wanted to change N. So N we start off as 10,000. I'm going to decrease this to only, let's do 50, okay? And I'm going to rerun all this code. This is all going very quickly, but I'm just recreating this plot. Okay, so PR has only 49 values now, and now you can see the jaggedy nature of this. It's plotting between the normal, Poisson, and gamma. Then it increments, the diagonal line brings us to the next PR, normal, Poisson, gamma, and so on. So if you ever get a really jaggedy plot like this, it's because you have not subsetted the data correctly. And if I run where I've assigned the aesthetic of color equals variable, now it's plotted correctly. Okay, things aren't still great with this plot, right? Because it's too coarse, and so this step function has diagonal lines instead of a step function. Okay, there's other issues with this, but that is a major issue with plotting, and so I wanted to point that out. That may save you hours later in your life. All right. Another thing you can do is, all I've done here is look at a certain subset. Okay, so rather than specifying the data frame quant melt inside as the argument, which was the previous, okay, here's quant melt with the previous plot. Now I just want to look at the left tail. So I'm going to specify a subset only where PR is less than 0.01. And so here, PR is 0.01 in the bottom right-hand corner. We're just looking at those first several values. Okay. So you can, all I'm saying is you can pass a subset in as the argument as a data frame. All right. One more plotting example. Let's generate some random numbers. So remember n was 10,000, and so I'm going to specify an index column, which is going to be the numbers 1 through 10,000, and then I'll have the normal Poisson and gamma random variables, and those are all going to be R is the random number for the normal distribution. So if we look at the summary, I have an index which is just gives you the 5-number summary you'd expect, and then here's the quartiles for the normal distribution, Poisson and gamma based on random sampling. All right, let's plot that. So ggplot rands, I didn't point this out, but if I page back up, rands is the name of this data frame. So that's the data frame I'm going to use, and then I'm going to add to that 2 objects, or 2 layers in grammar of graphics language. One is going to be the density, and I'm going to specify the normal. So this norm is a column within rands. I'm going to assign that to X and fill that with the color red. So that's this red hump here, and the alpha is 0.05. I'll point out that there's a line that is black. That is the aesthetic of color. The aesthetic of fill is the red here, the area between the line and the axes. Okay, that's fill. Then I've added, here's a plus sign, I've added another layer, which is the density for the Poisson. Okay, and I've plotted that. All right. Ooh. Well, this was because RANDS was a wide data set, and so I had to specify a separate column each time. But there's a much better way. If I make my data long, then I can do this in one step. So if I melt the data frame, so here's RANDS, and here's another way of specifying this. Previously I specified an ID variable, and the ID variable is something that would occur for each of the other columns that are being stacked on top of each other. If I instead, so I recommend looking at the help for melt, and in particular, if I go over to R and go to the console and look for the help of melt, I actually want melt.DataFrame, and it will give you the help for specifying the ID variables or the measurement variables as different ways of indexing or specifying what columns get stacked and which columns get repeated over and over. So here measurement variables indicate that I'm going to stack these three columns, the norm, Poisson, and gamma, and so I do get in my melted data frame, I get the index variable, which will repeat over and over again. The variable takes the label of the column names, and then the value is the value under the norm column, and so on. So with my new ggplot command, I can say, let's put this melted data frame in here, assign X the value, and the fill is going to be the colors, and that's going to take the variable column. So if I page up for a second, value is the thing that's going to be plotted along the x-axis, and variable is how I'm going to distinguish the three curves I have. So fill is the three variables. So I have a variable over here which has a key or a legend, and this is the norm, Poisson, and gamma. And so we have those three colors. And what I'm plotting is the geometric density, or geometric object is the density, and with alpha of 0.5, which allows me to look through the curves. It means the opacity is 1/2. All right. Finally, notice for this figure I have a caption. Much better. Now, what do we have? Why do we have a stegosaurus? So in knitr, I specified in the chunk option figure caption equals much better, and so on. And that created a caption for my figure. Now, I'll be honest, this doesn't work that well for slides as I'm doing it. Notice there's no figure number, but if you're not making slides, and almost none of you will be doing this, then you'll get a figure number here, and you'll be able to cross-reference that within your text using LaTeX. All right, so let's answer this question. Why do we have a stegosaurus? Right, so a stegosaurus is all right, that's a stegosaurus. It's a dinosaur with lots of dangerous fins on its back. So why is that? Why is this green one pointy like this? So that's for the Poisson distribution. The Poisson is a discrete distribution. The only thing I've done here is I've changed within the geometric object density. I've changed the adjust to 0.5. So I've narrowed the density kernel that's using to smooth the density, right? So Poisson is a discrete distribution. It has a point mass at the integers, and so each of those point masses is being smoothed over with a small narrow Gaussian kernel. And so the problem here is that we've mixed two continuous distributions, the normal and the gamma, with the Poisson, which is discrete, and we're trying to plot them all in the same way. Probably what you want to do for the Poisson is have vertical lines that go up to the point to indicate these little spikes of point masses. Oh. And it doesn't matter how pretty a figure it is, if it doesn't make sense. So it is possible to, within one plot, create two layers, one layer with the smooth curves for the continuous distributions and another layer with point masses for the discrete curve. But that's something you'll want to think about how to do. All right, the last idea in this lecture, which we will revisit because it is so important and powerful, is the apply function through using the apply R package. So the idea here is to take a data set, split it into subsets. For each subset, apply a function, and then apply or combine the result of each of those subsets. So our example here is to look for the quantiles of each distribution. So here are the 5 values that we want to get the quantiles for. Okay, 0, 0.25, 0.5, 0.75, and 1. Those are the quantiles. And if we apply the quantile function, and by the way, if you look at the quantile function, there's like 9 or 11 different ways to compute quantiles. The default is typically fine, and it rarely makes a difference, but you will find that if you use a quantile function, it does not match the 5-number summary that you would expect. Okay, so in the RANDS data frame, we have a normal column for the normal distribution, and the probabilities that we want to extract the quantiles for are these 5. So my probs. That's going to go into quants.norm. And here is for the 0, 25th, and so on quantiles. Here are the values of the normal distribution that gives you that CDF value. Finally, how would we get this for all 3? Well, we could repeat this line 3 times, one for each of the normal Poisson and gamma distributions, or we can use this strategy of splitting, applying, and combining. So ddply is probably the most important apply function in the plier package. The dd indicates that a data frame, the first D indicates that the input will be a data frame, and the second D indicates that the output will also be a data frame. So you can have DA ply, for example, if a data frame was coming in and then an array was coming out. And there's lots of other combinations. So rands.melt is the long form of the RANDS data frame. It has a column called variable, and that is what we're going to use to split or subset our data frame into. Okay, so rands.melt is a long data frame, and you can imagine grabbing the top third, which is the normal distribution, the middle third is the Poisson, and the bottom third is the gamma. And that is being split up by the variable, which has those names, norm, pois, and gamma. For each subset that we've broken it up into, we're going to input it into this function that we're going to define. And x, this x is the input name for that subset. Okay? So the first time through, x is the top third of the data frame associated with the norm distribution. So remember, the second D here is a data frame, so we have to create a data frame. So the data frame we're going to output is going to have two columns. One is going to be prob, and the second is quantile. My probs are these 5 numbers. So there's going to be 5 rows there. And then the quantile column will calculate, just as we did up here, the quantiles of that distribution. But now the distribution that we're looking at is X. The first subset is those normal values, and the value column. So from the value column of the normal distribution, we're going to calculate the quantiles for these probabilities and put that into the quantile column. Then ddply is going to do that for each variable. So we're going to do it so then X will take the subset for the Poisson, and it will calculate it for the Poisson, and then it will do it a third time for the gamma. And the output is going into quants.all. Let me page down. Here is our result, quants.all. So it has variable. Where did the variable column come from? Well, the variable column is included because it's the variable that it was subset on. It was not part of the data frame down here, but it is a critical variable to have in the output because we were subsetting on that variable. So we have a variable column, so we have norm, Poisson, and gamma, and for each of those we have the probability column, 0 up to 1, and so on, and then the quantiles. Beautiful. That just saved you a ton of programming if you were trying to do this on your own. And it is pretty fast. And if you can do parallel computing, because this is what's called an embarrassingly parallel operation, you can do this in parallel if you have a very big data frame with many categories. All right. The last thing to point out is that there's lots of chunk options within knitr, and we mentioned briefly the figure caption one. There's also ways of specifying the size of your figures with figure width and figure height, and there are also ways of specifying the output size, which is like out width and out height. And I'll talk more about that in class.